Good morning, everyone, for distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Ziming Zhao, Associate Professor and Director at Khoury College of Computer Science, Northeastern University Boston. The title for today's talk is Securing the Bad Metal, Control Flow Attestation and Pitfalls in Microcontroller System Design. Dr. Zhao his research interests include systems and software security, network and web security, and human-centric security. His research has been supported by NSF, Department of Defense, Air Force of Scientific Research, and U.S. National Centers for Academic Excellence in Cybersecurity, which is also part of NSA. He's also a recipient of several awards, including NSF CAREER Award, NSF CRII Award. His research outcomes have appeared in a number of conferences and journals, IEEE S&P, namely USENIX Security, ACM CCS, NDSS, ACM MobiSys, ACM/IEEE DAC, IEEE RTAS, IEEE TIFS. He's a recipient of the Test of Time Paper Award at ACM SACMAT 2024 and Best Distinguished Paper Awards from several prestigious conferences, including USENIX, ACM AsiaCCS, ACM CODASPY, and ITU Kaleidoscope 2016. He earned his bachelor's and master's degree from Beijing University of Post and Telecommunications in 2006 and 2009, followed by a Ph.D. in computer science from Arizona State University in 2014. Dr. Zhao, it's an extreme honor to have you as part of the webinar series at UND. Thank you so much for taking the time this morning with us to share some insight on this topic. The floor is yours.
Thank you so much, Dr. Raghunathan. Thank you so much for inviting me, and I'm very happy to share my recent research. Can you guys see my screen right now?
Yes.
Perfect. First of all, I want to say sorry for missing the last webinar. It was that day I was in Buffalo, upstate New York, and we had terrible weather that day, and we lost the electricity for some time. And so when I joined online, I was like maybe 10 or 15 minutes late, and you guys have left. So sorry about that. I apologize for that. So hello everyone. My name is Ziming Zhao. I'm an associate professor at Northeastern. And I direct my own lab. I call it CactiLab because I lived in Phoenix for so many years. We do all kinds of research in cyberspace security and also forensics. So today, I will give you a peek into what my lab has been up to. I will discuss two main projects on securing microcontroller-based systems. Actually, neither of the papers has been published yet, but we almost finished both papers, and I'm just eager to share with the world what we have been doing. So before we jump into the projects, I would like to provide a brief overview of my research. My research interests primarily revolves around the broader concept of cybersecurity. I've been engaged in all kinds of research spanning system and software security, network and web security, and also human-centric security. So in each of those three domains, we published many papers, and we got some fundings as well. So this slide shows some keywords of our research and also some of our recent publications in those areas. But my true passion and our lab's focus right now is still system and software security, especially for IoT and embedded systems. So we are actively involved in developing innovative, at least we believe it's innovative, security solutions to fortify those systems, as well as identify hardware design flaws and software vulnerabilities within them. So our primary focus revolves around four different system-on-chip platforms. And the first one is microcontroller, which is also the focus of my talk today. So those microcontrollers, they are very affordable small CPUs. So one of the most popular microcontroller class is ARM Cortex-M. Then they are widely used in low-end IoT devices, including insulin pumps, all kinds of sensors, drones. From a hardware point of view, this kind of CPUs, they lack a memory management unit, MMU. So MMU has been a fundamental component of our modern operating systems. And a lot of our modern security solutions also build on MMU. For example, address space layout randomization. If you do not have an MMU, it's very difficult to get enough entropy to randomize your address space, right? So to respond to this kind of challenge without those hardware features, our research is mainly about finding other alternatives, hardware features, such as trust zone, memory protection unit, and other new instructions to secure such devices. So besides microcontrollers, we also work on traditional desktop and mobile platforms. We focus on Intel and also ARM Cortex-A devices. We have been working on trusted execution environments, side channel attack, how to mitigate side channel attack, and also Linux kernel hardening using some specific hardware features provided by these CPUs. So one of the hardware feature I'm really into in the last months is something called user interrupt from Intel. So this feature will allow two threads or two user processes to communicate with each other without entering into the kernel. So I feel this is a very interesting feature. First of all, we can use this feature to build faster systems, faster secure solutions, and we can also identify many security issues of this hardware feature itself. For example, we have a lot of security gateways, security solutions deployed in the kernel. Now we have a new hardware feature, user interrupt, to bypass kernel. Then how do we deploy? Where should we deploy those security solutions? So that's something I'm thinking in the last months. I'm not an expert on this topic yet because I only heard about this feature several weeks ago. I feel this is fascinating, so I'm starting that. Besides that, we also work on FPGA systems and other kind of accelerators. One of the projects we did before is to use FPGA to build your own trusted execution environment. So some of you may be familiar with SGX, TDX from Intel, Trust Zone from ARM. So those are security features, trusted execution environments. But our argument is those systems, to use those systems, you still trust Intel, you still trust ARM, you trust their hardware. What if you don't want to trust those third-party vendors, right? What if you want to build your own trusted execution environment from scratch, from hardware layer, from the circuit layer? That's why we develop a system that build your own TEE with FPGA. So this slide somehow summarizes at a very high level our research methodology and what kind of systems we usually use. I would say our research methodology is about exploring both the potential advantages and also pitfalls associated with new hardware and instruction set features. At the architecture level, we work on ARM, Intel, FPGA. Then a lot of our development is on the OS layer, firmware layer. I teach OS class at Northeastern. I also teach software hacking class at Northeastern. Then our development is OS and also compiler level as well. So we mainly use LLVM because it's much easier to develop. So today I will zoom in two of our recent projects. They are kind of about microcontroller systems. Like I said, neither of this has been published yet. So before we jump into the project, I give you a little bit background about what is microcontroller. So I already talked about a little bit about this. So they are CPUs without MMUs. Usually they are RISC architecture, and they are commonly found in low-end IoT and embedded devices. They were deeply embedded before. So the attack surface of them was kind of small. But however, now they all have internet facing interface. So they are facing all kinds of attacks like all other systems, desktop, phones. And they are extremely popular. It is estimated that the world has already over 250 billions of such microcontrollers. And my lab, we mainly work on the Cortex-M microcontroller. And in the 2020 fourth quarter alone, just that quarter, more than 4.4 billions of those CPUs were shipped. So they are actually everywhere. In our modern cars, there are 20 to 50 of those kind of microcontrollers. From hardware side, like I said, they are usually RISC architecture using Cortex-M as an example. They have 16 general purpose registers. They do not have MMU, which means everything lives in a 32-bit physical address space. So this is like our desktop system 40 years ago. So we have developed all kinds of security solutions for our desktop server systems in the last 40 years. So we cannot easily port those security solutions to the system because they do not have the hardware features we need. Sometimes they come with some security features. For example, Cortex-M also comes with a trust zone, but it is much different from the Cortex-A trust zone. It is streamlined. Actually, in one of the papers we published in DAC 2 years ago, we find out that the streamlined security feature trust zone in Cortex-M will introduce new security attacks. It will be a control flow hijacking attack, which is not possible for Cortex-A. So even if they are security features that are designed for security, it do not mean they are trustworthy or secure. We try to find the problems there. At software layer, most of those systems are still developed in memory unsafe languages like C. We do see a shift of Rust, but I think it will take still maybe several years before we fully adopt Rust. And also Rust has its own security problems, not necessarily memory safe problem, but other security problems. And surprisingly, and also probably not that surprising, most real-world microcontroller systems, they do not even adopt privilege separation. So the CPU does support privilege separation, but we dumped thousands, maybe 3,000 real-world IoT devices and analyzed their firmware. Only 2 or 3% of them are using the privilege separation. For 97% of them, everything runs in the privilege level. It's like in your desktop, everything runs in the kernel level. So one bug will fully compromise the whole system. So a lot of functions, they are just implemented in interrupt service routines. So you can say that there is a huge gap between the security of such systems of the state-of-art desktop or server systems. So the first project I want to talk about today, I call it EDONA, Efficient Control Flow Attestation for Embedded Systems. So this is a follow-up work of our previous HOMES project. We have a Sherlock project to do control flow integrity for such systems. We have a Mycroft project to find cross-trust zone control flow hijacking attacks. We also have a Watson project to do shadow stack protection for such systems. This one, EDONA, is about control flow attestation. So let me explain a little bit what is control flow attestation. So the concept was first proposed in CCS in 2016. This figure is actually from the paper CFLAT published in CCS. So this figure describes one way to implement control flow attestation. The goal of control flow attestation is to prove to a remote verifier that the application, the code, the program running on my machine follows some predefined control flow graph, which means if there is a control flow hijacking, there is a buffer overflow attack, there is a ROP, return-oriented programming attack, then the prover will not be able to successfully prove to the verifier that such attack didn't happen, such compromise didn't happen on my computer. So that's a basic idea. So this figure depicts one way to implement that idea. There are actually many other ways to implement the idea, but they all have some problems. Let's say one of the easiest way to implement this is the prover will send the full trace of its program execution to the verifier. The full trace here could just be all long-sequential control flow transfers. In a program, if there is no long-sequential control flow transfer, it means the program will keep executing the next instruction. Then for long-sequential ones, like a jump, like a function call, like an interrupt return, or just a regular return, you do not execute the next instruction, then we call that a long-sequential control flow transfer. So as long as the prover can send all the long-sequential control flow transfer destination address to the verifier can verify the full trace, right? The problem with this approach is even for a super small program, let's say we just have a very simple loop, but the loop can run forever. Even if it's just a simple program, the trace could be unlimited. The size of the trace could be unlimited, right? Another way to do it is we compute a measurement on the trace. The measurement can just be a hash function, a keyed hash function to generate some hash value on top of that. So in the naive trace-based approach, we send a full trace, then we do not need to send the measurement. So the verifier can just abstractly execute the program for each destination to say if there is any illegal control flow transfer. So the trace here could be large. The measurement actually here could be small, it's a constant size. So in the SafeLab paper, which originally proposed the idea of control flow attestation, their approach didn't send out any trace. Instead, they send out a lot of measurement. They compute the measurement of each pass, and there could be a lot of paths, exponential to the number of basic blocks. So in this project, our goal is to reduce the data transmission between the prover and the verifier. Actually, it's a one-way data transmission from the prover to the verifier. And the data has two parts. One is trace, one is measurement. So all previous approaches, they are either huge in the trace or a measurement. In our approach, Enola, we designed the first approach that we reduce the size of the trace to the linear to the number of basic blocks. And the measurement is only a constant. It's just two measurements. So that's our goal of this project. So to achieve this, we propose something new. We call the basic block occurrence trace. So this trace basically records how many times a basic block has been executed. And we also have some indirect destinations that is not in the control flow graph. However, we limit that to a certain number to make sure this part is the size is constant. Then for the forward pass, which means call, jump, those kind of passes, we calculate one measurement Then for backward pass, which means the return, we compute a larger measurement. And we implemented this using a new hardware security feature called pointer authentication on Cortex-M. So this feature has been proposed maybe 3-4 years, and there has been a lot of research using this feature to maintain the integrity of memory objects, such as return addresses on the stack. We actually have an ongoing project using this hardware feature to maintain the integrity of Linux kernel credentials. So Linux kernel credentials, they are very important data structure. They record the privilege of the tasks on your system. We use this feature to protect that. So in particular, for this project, we are using the Cortex-M version of this, and we are using the PACG instruction, a general purpose, which use a general purpose register to store some kind of a PAC value or MAC value in this case. We use that to replace the software-based hash operations. So this is the workflow of our system. So our system takes C code as input. The C code goes into our compiler. Our compiler will instrument the binary code to, in particular, we instrument those PAC instructions to make sure that we are reporting the basic block trees and also compute the measurements. So after that, it goes to a code scanner to make sure there is no dangerous rob gadgets. Then at runtime, the attested program executes in the normal world of the trust zone, and we use a PAC hardware to compute the measurements. And the tested program with instrumentation will also report its traces to the secure world. The secure world is trustworthy in this case. Then the secure world will generate the measurement report, attestation report with 2 measurements and send to the verifier. And the verifier will do abstract execution to recover the control flow and measure if the control flow is legit. So here is an example of how we instrument the direct calls. In this case, the blue lines, they are instrumentations to report the occurrence trees, and other green lines are those. The blue lines are to update the measurement. As you can see here, we're using the PACG instruction to compute the measurement, and to report, we're using this report direct function is actually an interface from the secure world. So this is for the direct call. We do something similar for indirect calls and for return instructions as well. So all of those implementation is at LLVM level. We write LLVM process for this kind of instrumentation. We evaluated the system. First of all, we compare how those instructions are faster than software implementation of hash functions. We use some popular hash functions in embedded systems. For example, Blake 2 is widely used in embedded systems. Even for Blake 2, running on Cortex-M, it takes almost 8,000 instructions to compute the hash. However, using the PAC instruction, it will only cost 12 cycles. So this is like 4,000 times faster at this level. But our goal, obviously, is to reduce the data transmission. And the figure here shows how our data transmission is much, much smaller than the previous papers. So we compare with BLAST, which is a paper published in CCS last year. I want to single out this one. Our approach is linear. Our data transmission is linear to the number of basic blocks. So for this one, we are only sending out 168 bytes of data. However, for the same program BLAST, it is sending 250K bytes of data. That's much, much smaller. It's also yeah, almost 1,000 times smaller for this particular case. Because the problems of previous approaches, they cannot actually evaluate it on bigger programs. So they were only evaluated on very small programs. And our approach is the first one evaluate on some real world crypto programs like AES, MD5, RSA. As you can see, previous approaches, they didn't evaluate. So in summary, this is the paper we are submitting soon. We minimize the data transmission in control flow attestation for the first time achieving linear space complexity for this problem. And also using new hardware features, we achieve a lower or comparable performance to existing work. So any questions for the first project?
We can reserve the questions at the end, so
okay.
we can.
Cool. So the second project is a little bit soft compared to the first project. This is about the insights, the lessons we learned in securing microcontroller systems. Especially we learned this from our experience in participating the MITRE embedded CTF competition. So we have noticed that a lot of existing work are focusing on analyzing real-world firmware of those microcontroller systems in order to identify and characterize the vulnerabilities. Our team has been doing that as well. Like I said before, we crawled thousands of real-world IoT firmware, and we find their vulnerabilities. We find the lack of security features in those software. And we have published a paper last year in WOOT, Offensive Technology Conference with USENIX last year. However, no one really understands why we are not using the existing hardware security features. For example, why we're not using stack calories, or whether we're using stack calories correctly, or why we're not using other security features. So my team has been participating in MITRE embedded CTF for over 7 years, I believe. So every year I will form a team with undergraduate students, master students, and sometimes my Ph.D. students will also participate in this competition. Each year we were in this competition, we will design a secure system. Then we will submit the secure system to other teams for them to attack. And we will also attack this other team systems to capture flags. And we think this gives us a unique perspective to understand what developers are thinking when you design a secure system. Especially this is a security competition. So security is like the first citizen here. People think about security. In real world microcontroller system designs, people do not necessarily think about security. So this will give us unique insights into why it is so difficult to secure such systems. So I think I can also encourage you guys to participate in this competition. This is like a semester-long competition every spring semester, but you can get started, get prepared from the fall semester. Usually there are 3 stages. The first one is the design stage, where MITRE will tell you what is the security goal of this project. And usually they will also provide a reference system. However, the reference system doesn't include all the functionalities, and it doesn't implement any security features either. Then it's your job to design and develop your secure system and hand over to MITRE. The MITRE will test your system, but they will not test the system for security. They only test it for functionality. Then MITRE will hand over your designs to other teams. Then they will analyze your source code, analyze your binary code, and think about how to attack your system and capture your flags. You will do the same thing for other teams. So this is another figure of workflow. Basically, MITRE will give you several development boards Some of them can be only used in the attack stage because they have secure boot, they have keys to protect the flags. And also MITRE will embed the flags to the system. So no one but MITRE knows the flags. And as attackers, it's your job to capture the flags. So previously, we have designed all kinds of embedded systems for this competition. Last year, we designed a car fob, which has a car component and a fob component, and you can do man-in-the-middle attack and other attacks. In 2003, we designed an insulin pump. 2021, a drone system. Personally, I enjoyed several competitions. One of them is a gaming console we designed maybe 5 years ago. That year, we were the third place worldwide. My team were third place. That time, I was not in Northeastern yet, and the Northeastern actually won the competition. In that year's competition, you need to design the next generation gaming console on an FPGA-based system. And imagine you design a next generation Xbox. What kind of security features you want? You want the users to only play games that they purchased. You don't want them to play pirate games, right? You don't want them to cheat in the games. You don't want them to use your Xbox to mine Bitcoin. So those are the security features you need to design. What makes that years of competition interesting is they use the FPGA systems. And because of that FPGA system, that year it's very hard to secure the main Cortex-A CPU there. But there are only 3 teams figured out we can use the FPGA system to attack the Cortex-A system, including SAMU, including Northeastern, and also my team. I was at Buffalo that time, not Northeastern yet. So that's why those 3 teams captured all the flag of every team. However, Northeastern was the only team they figured out how to protect the system, also use FPGA. They basically designed an FPGA module to encrypt everything in the main CPU. When the main CPU wants to access memory, it has to go through the FPGA first, which is a very interesting design. Because of that, SAMU and my team didn't capture any flag from Northeastern, and Northeastern captured everyone's flag. My team has been doing this for a long time, and usually we are top 5, top 6. We were placed in top 3 twice. This year, I have a totally new team, so we're not doing very well this year because they are all new undergraduate students. But I think they enjoy the competition. This is something I think you guys can also do. There are hundreds of teams participating in this every year now. So for this research, for this paper, we analyzed 47 unique team submissions in the last 2 years. We analyzed their source code, we analyzed the document, their make files to understand how they design this system and what kind of problems they may have encountered, how they addressed that. And we take this one step further. We try to understand why they make those kind of design choices. To do that, we conducted 22 semi-structured interviews with participants from 19 teams. Here is a table list those participants, how experienced they were in the competition, at which stage. You can say most of them are undergraduate students, a second year, third year, even some freshmen there. And some of them are very experienced Ph.D. students. For example, this guy, P13, he's very, very experienced. Right now, he's a professional hacker. He's an independent hacker. I know him personally. He was a PhD student. He put too much time on hacking in all kinds of competitions, including this. So he didn't graduate. He didn't get his PhD, but he got his master's degree. Now he's just an independent hacker doing some contract job to hacking for companies. Of course, ethical hacking. He more like a pen testing, right? Yeah. So we had a lot of findings in this. First of all, like I said, we find that even in this competition, none of the 47 submissions adopted privilege separation. This is consistent with what we found in real-world firmware, where only 2-3% of the firmware use a privilege separation. So then we ask them why you are not using privilege separation. This is a concept you learned from your operating system class in the second or third year, right? So most of them will say that they thought there is no operating system in such systems for such Cortex-M microcontroller systems. So privilege separation is not useful, right? So this is obviously not the right mindset. We should always choose the best design, right? Another thing is about memory wiping, which means you read some secrets from some secure storage, save that in the memory, but after you use that, you probably want to erase them from the memory. So even if there is a memory leakage, there is a cold boot attack, your secret will not be disclosed. We find out that many teams actually they attempted to implement this feature. However, none of them realized, not none of them, most of them didn't realize the compiler optimized away their memory wiping code. We find out this by looking at the source code and their binary code. But they trust their compiler. They implement everything in their source code. They never check their binary code. So that's also very interesting. So here is one example. This is an implementation from a very good university. They use the memory set to wipe, erase some sensitive data from the memory. So hopefully it will not be, it can defeat cold boot attack or whatever. We actually find out that the most important memory set they were using there, the second one, was optimized away by the compiler. And the compiler didn't give any a warning or message saying I'm optimizing this away. So this is also the compiler designer's fault because they do not really understand what is the intention of the developers to have this line of code. They only do program analysis to realize this piece of memory was not used, was not referenced afterwards. Then this memory set is not really necessary from functionality's point of view, but from security point of view, this is necessary. That's the intention of the developer, right? We also find out that several teams use the security feature called reload, which is relocation read-only feature. This is a feature widely used in our systems right now, but they are mainly used for application levels. This one makes sure that global offset table after your program is launched, after the pointers in the global offset table is resolved, the global offset table will set as read only. So attackers will not be able to change the value there. However, for such systems, there is no such thing as global offset table. So the participants in this competition, they used this feature, they assume their system is protected by the feature, but actually is not doing anything. And the compiler is not giving any warning or explanation to the developers. Another example, or more extreme, is the non-executable stack example. So this is a feature that all our modern compilers implement, LLVM, GCC, all implement this. So basically, this is to defeat code injection attacks. In a traditional buffer overflow, you override the buffer and you override the return address on stack. And also you put your share code in your buffer. You put your share code maybe at an address lower than the return address, could be also be higher than the return address. Anyway, your share code is placed on the stack. You can also place your share code in environment variable, right? That is also on the stack. Then the hardware feature here is, the CPU feature here is to make the memory readable only, but not executable in this case. So you can read the stack, but you cannot execute from the stack, which makes sense because why do you ever want to put any executable instructions on the stack? You don't want that. So how this is implemented is there is a compiler flag, compiler option to you can use, which tells the compiler to mark the L file header, saying that the stack should not be executable. But after you compile, you get an executable file, which is a file. It's on a file system. It's not a running program, right? When you run this program, the OS, the loader, will actually load this program, will interpret the header of the L file and find out, oh, the stack should not be executable. Then the kernel will set up the memory management unit to make the stack not executable. That's how it works, right? However, like I said, in this system, there is no MMU. There is no memory management unit. If you only mark the L file, no one is going to respect that. There's no OS. So most people do not realize that. They think their stack is protected by only just using that compiler option. They didn't realize how everything works. So only several teams actually correctly implemented this by configuring the MPU on this system. However, another problem we find is in a desktop system, you have an L file, the L file has headers, but now for embedded systems, you don't even have L files. After you compile the L file will be loaded to the flash region of this device. And that loader usually will ignore those header information. So whether the stack region should be executable or not was not even stored in that flash in current designs. So which means the vendors should also fix their loaders for this part. So sounds like very serious problems here. Then we also identify some practical challenges. So practical challenge means the developers, the participants, they fully understand what's going on. They understand things correctly. However, they still cannot secure the system because there are some other challenges. For example, 7 out of 47 submissions used Rust in the 2 years, but they struggled. It's very difficult to make Rust running on the system, difficult to debug, difficult to write secure Rust code. And many actually just are using unsafe Rust, which has the same problems that C or C++ code has. So this could also be a huge research direction, and my team also want to work on this. Another practical challenge we find out is entropy sources. We find out that on such devices, first of all, there is no true random number generator, and many teams, they designed very creative ways to generate a better random numbers. They combined multiple entropy sources together. There are some analog peripherals on such systems like temperature sensor, light sensor. They combine those to generate more reliable entropy. However, there is no theoretical analysis. There is no theoretical guarantee that those entropy sources are actually safe, even when they are combined together. So the summary of this project, this is the first project that look at the overall life cycle of microcontroller system design. We're not only looking at the vulnerabilities in firmware, we also try to understand how those vulnerabilities were introduced there in the first place. What are the root reasons they were introduced? And we provide recommendations to developers, educators, compiler vendors, hardware vendors, how we can address those kind of issues. So those are the 2 projects. And we still have many other projects ongoing, especially for the microcontroller part. For example, this is the Watson project. We are using data, watch point, and trace unit to build faster and secure shadow stacks. led by my PhD student Saga, and my PhD student Gaoxiang is developing a kernel protection method using pointer authentication feature. This one we're building secure and fast shadow stacks using new hardware features, which is a debugger feature actually, data watch point and trace unit. We use that to develop shadow stacks. Let's say, you can see my screen, right?
Yes.
Okay, perfect. Then my PhD student Gaoxiang is working on Linux kernel credentials, also using the PAC authentication feature we also used in the previous Cortex-M project. We actually learned a lot in this project because kernel is such an amazing project with so many complicated components. And the challenge here is to make sure our new design is compatible with existing Linux kernel. Since this is a Linux kernel project, we open sourced this when we started it. So even right now, it is open sourced. We also work on some glitching. My student Joanne is working on clock and voltage glitching to attack microcontrollers. My student Jun, PhD student Jun, is working on using electromagnetic signals to assist the software fuzzing. We are interested in finding bugs, and fuzzing is still the most effective way to finding bugs. We're thinking about using EM as side channel to fuzz deeply embedded systems that we do not have source code, we do not even have binary code. For the future research, we still work on microcontroller and software system layer. We work on PR layer, kernel level, microcontroller architecture level, and we also explore other embedded systems. I just submitted a proposal to work on the security of mobile DNA sequencers. We're trying to bring a provenance to such systems, not only the cyber part, also the physical part. We want to design some DNA spikings to trace DNAs. My collaborator is working on the physical part, I work on the cyber part. We also work on GPU and also other confidential computing modules as well. I have 2 kids, so I worry about how safe our internet is for them. So I work on a little bit cyber crimes, especially cybercrime involve minors. My kids play Roblox, and we find out there are some unsafe content on those systems. We also publish that. Those are more like a side project, but also very interesting. I do a lot of CTF challenges. Not only I form teams to participate in CTF challenges, I host my own CTF challenge platform. So in Northeastern, I have a challenge platform. I design hundreds of challenges, especially for my software security and vulnerability class. Unfortunately, right now, this is not public. We're trying to make it public. The main reason for us to not making public yet is basically funding. If we make this public, we think there are thousands or 10,000 of people using this, and it will be very, very expensive to host this in any cloud infrastructure. And we do not have a very good solution for this yet. That's why we're only using this in Northeastern yet. But if you guys are into this, I can help you guys deploy our system in your infrastructure as well. This system has been deployed in multiple universities already, including University at Buffalo, Khoury, Buffalo. I actually put all my class lectures, everything on YouTube. So if you are interested in learning software security, you don't have to take my class. You can just learn by watching my videos, except you don't have the platform right now. Also, in Northeastern, we host capture the flag competitions. C2C competition is something country-to-country competition we host this year. I'm part of the team to host this. Several of my PhD students are also helping as well. So this competition used to call Cambridge to Cambridge, the CTF, because it was between MIT and the University of Cambridge before, but now it has been expanded, and Northeastern we're hosting it. We already had the qualified CTF 2 months ago. It was online. It was open to everyone. Sorry, I forgot to inform you guys, advertise this to you. I should have. Anyway, we have invited 100 students to the Northeastern campus for the final, which will take place in July. And I'm part of the team to do this. So thank you very much for listening. You can find more information about my research or open source project on those websites. And I'm very happy to take some questions.
Super fantastic, Dr. Ziming, for touching all aspects, and
Sure.
it's fascinating to see, your research. Also, you took time to put all these things on YouTube and the CTF competition. It takes a lot of time and energy. It's not,
Yeah.
and so that's kudos to, I think we would love to participate maybe next year whenever you're doing it, so at least we can keep us posted, and
Definitely.
we are doing a CTF. Partnering with Meta CTF, but at the same time, it's open for high school, also for college kids. It's, but also we have our own challenges. We're still learning. We did last year, but I think it looks like you have a more rigorous CTF challenges that may be interesting to participate and learn.
Yep.
Yeah. Cool. And I'll open up the questions. So folks who have questions, can you put your questions on chat so we could ask, maybe I'll start with a couple of questions. I think, first of all, I think I'd like to get in touch with the Speed 13 independent hacker. Maybe I would like to invite him for some kind of a workshop or something, so we can able to, he said he's an independent hacker, right? Maybe something that I'm interested to learn. And it's talking about this first part of the project that you said, I think you said that your BLAST versus ENOLA, your approaches is about 1,000 times smaller because you have this linear approach that you adapted, in terms of the number of blocks. And, are there any particular limitations that you notice, by making it, with, even though with the same size of data that BLAST NLA has compared, is there anything that you see some limitations in your work that you, in comparing apples to apples with what they have done? Yeah.
So obviously, this is control flow attestation has several sequential steps. First, you execute a program, you generate some kind of trace or measurement, then you send the trace or measurement to the verifier, and the trace or measurement you send to the verifier is some data, some information. Obviously, less information you provide, then the verifier needs to do more computation, or sometimes there may be a threshold there. Actually, I'm doing a theoretical paper to prove the threshold there. If you go beyond some kind of threshold, you are sending less information data than that. The verifier can never really verify what's going on, right? There should be some threshold. I'm trying to prove that. So in our case, our verification will be slower than BLAST, as I'm showing on this picture. But the complexity is actually the same. So for BLAST and for our program, the complexity are both exponential to the number of basic blocks. However, in practice, they will be faster. Yeah.
What about the number of pass versus from prover to verifier, comparing?
What do you mean by number of pass?
Pass,
Yeah. So technically, we can consider when you execute a program, you have one pass, right? Just one non-pass. Yeah.
And you mentioned there are two measurements for the verifier, MF and MB, and what are those two specific measurements? Could you talk about
one for the forward edge, another one
forward and backward. I see. Okay,
yeah.
I see. Okay, cool. It's also interesting to see how you got this 12 CPU cycles with 4,000 times smaller. That's a very
Yeah, it's just one instruction, so it's very fast.
I see. Okay. Now, in terms of the team that, or the four teams that you talked about that executed correctly the stack non implementation in the CTF competition, was there any time limits that they've given? Are there any? I'm trying to understand the competition structure in terms of each of these
That's very
particular.
good. Yeah, that's a very good question. So for this competition, the design phase starts at mid-January every spring semester. Then it can goes um, to early April. So basically, you can submit your design and implementation anytime after that. So only if your design and implementation pass the test by MITRE, you enter the attack phase. But if you enter the attack phase earlier, you accumulate more defense points.
Cool.
The whole
And
thing like 3 months. Yeah.
so super. You mentioned about, have you worked on directly with vendors for integrating some more library support on any of these processors, in your research, while we're doing this as part of funded projects or maybe courses, but or the competition. But hey, I found out this thing, and this, maybe communicating directly to vendor and with your team. Have you done that effort in terms of in
Yeah.
communication?
For this particular project, we have been so MITRE actually helped us to forward our findings to their vendors already. And in previous project, we one of our project to secure Cortex-A devices from cache side channel attacks, we actually worked with Samsung, and Samsung deployed that in their Tizen OS, which is not as popular as Android, but it comes with all Samsung devices, including smart TVs, smart watches. Yeah.
Mm-hmm. Cool. So in your initial slides, you talked about most of the functional implementation is on the interrupt service routines, right? And then, what opportunities going forward that future researchers are looking at and to see where do you see, these implementations should run or more in a secure way? Yeah.
Um, that's basically what we have been doing for the last several years. I think microcontroller systems needs different security solutions that are desktop and mobile systems. Some of the ideas we have in the mobile and desktop systems can be migrated to those systems, but we also need to carefully design. Some of the features, even migrating them doesn't make sense anymore. For example, stack corollary, we have a short paper arguing that we think the stack corollary mechanism is not going to work in microcontroller systems. Because imagine how stack corollary works for our desktop systems. Every time when a program is launched, the program retrieve a random number from the kernel or whatever, and use that random number as a stack corollary, and all the functions in that program will use the same corollary value. So if this program fork some child process, then the corollary value will not change, right? So actually in my software security class, we have a challenge to defeat corollary with such programs. So there are limitations of that, but the problem is even more serious when it is in microcontrollers. First of all, there is not much hardware entropy there. The random number you are getting is not that secure. Second, there is no concept of process. Most of those systems are bare metal. The corollary they are using could be generated when the device is booted, but it will stay the same forever. Some of the devices, after it is booted, they stay running for 5 years, never changed. Then we find several examples that the stack clearly was even hard-coded. Then if it's hard-coded, you figure out, you do a binary dump or whatever, you figure out what it is, then it's not protecting anyone. It's just another the emperor's new security feature. It's not actually doing anything. Yeah.
Sure. Super. The last question, I think, you mentioned the CTF platforms. As we have a couple of DOE projects. One of them is 3.5 million with ANL, Oregon National Lab. And we have our own dedicated Lambda server. We also have access to AWS cloud infrastructure. I am very interested to see how we can work together to host some of your CTF platform together jointly, right? And maybe
Perfect.
in some competitions next year, something like that, right?
Sounds
Maybe.
great. Please reach out. I will be glad to help.
Yes, that's all I have. But I think thank you so much for your time. I think you will receive a nice plaque from UND, a certificate from our dean, and we will also make this video available on YouTube after we edit a few things. But I think thank you so much for your time.
Perfect. Thank you
This
very much. Yeah, please send me the YouTube link. Yeah.
Yeah, I will. Take care. Thank you.
Thank you. Bye.